Okay, so here we go. Last time we were talking about this business right here is a picture of a nice example of where you might have previous familiarity with the idea of level sets, right? So the idea is that contour lines on a topographical map are actually level sets of the altitude function, right? And so we saw pictures like this, and you can use things like this to make good decisions on how to climb mountains, right? And so, for example, I would advise, if I were climbing the mountain and if I were here and I wanted to get to the top there, I would not go in the straight line that looks really hard. I would probably do that, right? Because notice then that there's no particular part of that path in which I gain a lot of altitude over a very short distance, namely it's not that steep. Right? So a lot of information, geometric information that you can infer about a function from a picture. Okay. Alrighty. So moving along from there, we've talked about graphs, we've talked about level sets, and let's think about now this function right here, a function of two variables. I emphasize graphs and level sets are different. Right? Different pictures representing the same function. So you can see right here how big the difference is. For a graph, we set the function equal to a new variable. Right? To make a level set, we don't. There is no new variable introduced at all. We just set the function value, the function equal to a constant. Eventually several constants. Right? So totally different algebra, right? And again, this idea that you have to set the output value of a function equal to a new variable, no you don't, right? So, like so, see, we really don't have to. Right? Okay, so two different pictures, and yet they are related, and they're related by the following neat observation, that if you take a graph, and if you take a horizontal cross-section of that graph, right? Horizontal cross-section says I'm gonna set z equal to a constant because that's horizontal, right? And that's what I'm going to do to my graph. Altogether, then, notice that this pair is the same, or at least equivalent to this in the first place. So what we have then is, even though graphs and level sets are different, horizontal cross-sections of graphs are level sets. So here's a picture of that in action. Function of two variables right here. Now we haven't talked this through yet, but we will momentarily as to what the graph looks like. The graph, again, what you get by setting it equal to a new variable z. This equation right here, I claim, is the equation of kind of a bowl. And we'll talk more about that again in a couple minutes. Okay. By contrast, level sets, again, what you get by setting it equal to a constant, that's what a level set is. These equations give you circles. So again, very different pictures. Two very different pictures describing in their different ways, describing the exact same function. Okay, but again, the connection between these, notice what happens when I take horizontal cross sections, right? Horizontal cross sections described by setting z equal to a constant. Again, those are horizontal planes, thus the term horizontal cross sections, right? And now I appeal to your geometric visualization skills. These horizontal cuts through this kind of green bowl, if you will, make, well, these circles. And they are the exact same circles that we were looking at there. Is that okay? Everybody happy with that? Yeah.
Do both of the circles have the same radius?
Oh, well, I mean, I didn't specify, detail. I just drew some arbitrary circles here. But whatever constant you pick here, right? Notice that's going to be, if that's the same constant that you have here, then setting x squared plus y squared equal to z, which then gets set equal to c, effectively gives you x squared plus y squared equals c. So yeah. Is that satisfying? Okay. All right, so related but different. All right, now we've talked about now several different ways to draw pictures representing a function, or you can draw the graph of a function, you can draw a level set, or typically several level sets of a function. And there's another thing, you can talk about what function parameterizes your curve. Right? So several different ways that you can either have a picture and find an associated function, or a function and make some associated picture. Right? And for a lot of this, we've been thinking, given a function, what are the pictures? In this example, we're going to kind of turn that around, and I'm going to say, here's a picture. We're going to, in particular, look at this equation right here. Right, that's a line. So given that picture, given this geometric object, what function is this a picture of? And the answer is it's a picture of several different functions depending on what kind of pictures are you talking about, right? So this is a graph of one function. It's a level set of a totally different function. And it is parameterized by yet a third completely different function. So, getting into the details here. Let's see here. Yeah, this will be good. So, I claim that this function right here, this is the function whose graph is that purple line. Now, how do I know that? Well, because I can talk about how to form the graph of this function. How do we form the graph of a function? We set the values of the function equal to a new variable. This is a function of just x, so I'll call the outputs y. This, then, is the graph of that function. And notice that graph is equivalent to the original equation. And we moved some terms around. We divided by a constant or something, right? I mean, these are morally equivalent. I mean, they literally have the exact same solutions. So I'm going to say same equation. Is that cool? So we found here, this is the function whose graph is my given line. Now, how would I identify what function has as a level set this line? Right? So forget about graphs. Now let's think in terms of level sets. I claim that this function right here does it. And again, I can demonstrate why, because I can straight up just write down a level set. I'm going to write down a level set of this g function. And specifically, I'm going to choose to write down the level set where g equals 6. And notice, this is exactly the same equation as we were given. Right, so the same line, still talking about the same line. There's only one picture in this example, right? This one line is the graph of that function. It's a level set of this different function. Now, why do we want to worry about this? And the answer is that, keep in mind, I've said this several times. I'm sure I'll say it many more. We're going to be talking about calculus in this class, and calculus takes different forms. It has different looks, different geometric interpretations depending on which kind of a picture you're looking at. So if you want to know something about this line that the calculus of graphs can tell you, this green function is the function that you need to look at, because if you're going to apply the calculus of graphs, you'd better use the function whose graph, right, is what you're interested in. Likewise, we're going to have a calculus of level sets. We're going to be able to talk about how to interpret calculus objects in the context of pictures that are level sets. So if those ideas, if you want to apply the calculus of level sets to learn something about this line, well, you better use this blue function, because this blue function is the one for which a level set is my original line. So, punchline then, if you're not careful about this kind of thing, if you're a little bit willy-nilly with your, graph, level set, function, whatever, it's all kind of the same, right? If you accidentally apply the calculus of level sets to the function whose graph is your curve, you get meaningless nonsense. Yep. So it is something you have to be really, really careful about, and make sure that you're extremely comfortably clear with what precisely do we mean by the word graph, what precisely do we mean by the word level set before you start deciding which function to do your calculus to. Okay. Last comment, and we'll do this eventually also. Here we go. This function here relates to this picture as well, but in, again, a third way. This is a parameterization of our curve. And so if I were to draw a picture of, what results, wrong color, or to draw a picture of what results from this, in other words, just plot the output points, again, same curve, or said differently, if I were to plug this in to that equation, the equation works, right? So yet another function that in its way describes this curve, and there is going to be a calculus of parameterizations. So all three of these different sort of relationships between algebra and geometry, make sure to keep them distinct in your mind. Okay. All right, and that's basically what all this stuff here says. Yes?
How do you get the 32
Yeah, so the great question. I can generalize your question to how did I find all of these different functions? And you know what, I'd better not erase all of this. I actually kind of need some of this. Let me erase. I didn't want to do that. Okay, so let me start with the graph part of the question, right? So how did I get this, right? And keeping in mind, well, I wanted it to say y equals, because that's what a graph is, right? But I also wanted it to be equivalent to what we're looking at here. And so one way to say that is, what I did is I took this y right there and I solved for that y, which I accidentally erased. Sorry about that. This is that y. So if you solve for that y, that gives you this equation, which therefore gives you a function whose graph is that line. Does that make sense? Mm-hmm. Okay. I think the level set one is a little bit more obvious. It's right there, right? Sometimes the fish just jump in the boat. If you want to rewrite 2x plus 3y equals 6 as something equals a constant, it's already written that way. So that's a freebie, right? The last one, how did I find the parameterization? Your original question. Chapter 1 methods tell me that I can take any point on my line, such as this one here. This is given, right? Just given in the picture. Right? And then I can take any vector parallel. Let's see here. I will use. I'm running out of colors. What color have I not used? I'll use black. Okay, how about that? Any vector parallel, and just by kind of subtracting these 2 points here, I can subtract and get this vector. Right? And then those two things together, knowing this point, knowing that direction vector, then A plus TV gives me this formula right here. Yeah. Okay. Moving along. Okay, so this is a neat little bit of algebra right here. A very clever move. It's going to look pretty trivial at first glance. You look at this algebra right here. What's the difference between these two equations? And practically nothing. I took this term on the right. I've subtracted it over to the left. Barely anything happened. What's nice about this equivalence, right, these being equivalent equations, is that the top one is written as a graph. Right? It's written as variable equals function of other variables. That's a graph. And so specifically, whatever this equation is in purple, I can view it as being a graph of that dark green function. Okay, fine. This one down at the bottom, this is written as a level set. Again, keep in mind what a level set is. A level set's what you get when you set something equal to a constant. This is written as something equal to a constant. Critically, though, it's a different function. Right? So what I've got here then, two equations that are practically identical, certainly equivalent. One allows me to view whatever this surface is as being a graph. The other allows me to view the exact same surface this time as being a level set. And I'm going to point out that for any graph equation, you can always do this. Any equation that looks like this one right here, you can always take the right-hand side and subtract it over to the left-hand side, and you always get stuff equals 0, which is a constant. Right? So the nice punchline is, again, this little trivial little bit of algebra doesn't look like hardly anything, but it shows that every graph is a level set of a different function. Which, let me say that differently. If you find yourself looking at a graph of one function, but the calculus of graphs doesn't give you the information that you need, if you wished that you could use the calculus of level sets, cool, no problem. That function whose graph you're looking at, do this little move, and now you can apply the calculus of level sets to this new function. Very importantly, not the same function. Clearly a different function, right? This is y minus f, not just f. So the calculus of level sets applied to the second function will give you information about the original graph. Okay, and a quick example. For whatever reason, suppose you're interested in the graph of that function. And many different circumstances could lead to such a scenario, right? We've got some function, we're interested in its graph. How are we going to understand this graph? And calculus of graphs will tell us some things. But at the cost of a really easy little algebraic move there, I can rewrite this as being a level set of this other function, and the calculus of level sets applied to this second function will give us different information that could also be used. Everybody happy? Bad news. This is a one-way deal. Every graph is a level set. Not every level set's a graph. It's just unfortunate, but c'est la vie. Here you go. Here's a level set. All right. This is a level set of the function x squared plus y squared. Easy picture to draw. And it fails the vertical line test. Not a graph. Game over. Right? So, like I say, it's a one-way deal. If you're looking at a level set, it may or may not be a graph. Everybody happy with that? All right. Okay, moving along. There's a few tricks that I want to show y'all about how to understand surfaces in 3 dimensions. Y'all have done a kind of a 2-dimensional version of this before, something that y'all talk about in high school algebra and calculus classes. Is if you have an equation of 2 variables, how do you figure out what that curve is? And, various different techniques that you may or may not have seen. One of them is just to recognize various things. You recognize parabolas and hyperbolas and ellipses, and you could, if that equation happens to be a graph, then you can talk about the calculus and look at slopes and concavities, and you got various different techniques. So we're going to do kind of the same thing now in 3 dimensions after a fashion. Just like with the 2-dimensional case, we're not going to give you a completely exhaustive, 100% guaranteed, works every time answer to that question, because we just can't. There's too many different kinds of equations, and sometimes they're just really, really hard, right? So certainly that was the case in 2 dimensions, right? When you're doing XY plane plotting equations, there's some weird equations sometimes that you just can't get your hands on. So again, this is going to be a sort of a tools for your toolbox kind of a deal. And here's the first tool. It's this observation right here. This is the key part of it anyway. If, and this is a big if, this will not always be the case. In fact, depending on how you count, this will usually not be the case. But reality is it tends to come up more often than you would expect. That said, if your equation involves x's and y's only as part of this form right here, square root of x squared plus y squared. So x and y appear in your equation only as part of that expression. There's no stray x's. There's no sort of e to the x anywhere, nothing like that. If that happens, you get this powerful punchline, rotationally symmetric about the z-axis. And this is another one of these awesome theorems that's it's awesome because of the fact that it's so easy to check the condition. Eyeball glance. Look at your equation. Do you see any stray x's or any stray y's that are not part of exactly, specifically this form? If there are, too bad. You can't use this. But if there aren't, if x and y appear only in this special form, it's eyeball glance easy to confirm. And at the cost of that eyeball glance, you get this powerful conclusion. You have a rotationally symmetric surface around the z-axis. Now let me try to persuade you that this is true. Let's see here. Let's look at a point here. That point's got an x, y, and a z. And now I'm going to imagine rotating. Let's see here. How am I going to do this? You're going to imagine rotating around the z-axis, which produces a bunch of other points, but let's focus our attention on this one. We've got a purple point, we've got a red point, and here's the thing, they have totally different x coordinates, they have totally different y coordinates. It wouldn't appear they have much in common particularly. However, even though they have different x and different y, they do have the same distance from the z-axis. In other words, they have the same value of this expression, square root of x squared plus y squared, that we've agreed is the only way that x and y's matter in this scenario anyway. Right? And they also have the same value of z, again, because of how they were generated, right? One's a rotation of the other, and that doesn't change the z coordinate. So same z as well. So these are different points with different coordinates, etc. But the only thing that goes into the equation, apparently, is this expression, in which these 2 points are identical, and this coordinate z, on which these 2 points are identical. So these 2 different points, they either both work or they both fail. Yeah?
But wouldn't this only be valid if you equated the root of x squared plus y squared to a constant?
No. X squared plus y squared, square root of x squared plus y squared, it can be just a variable, a part of an equation. It doesn't have to be constant. The point is that any 2 points that are rotations of each other will have the same value of that expression. But I mean, there could be other points somewhere else that have different values. I'm just trying to compare just these 2 points. Does that make sense? Yeah. Yes.
So this is true because we basically converted that component into cylindrical coordinates?
Well, that's another point of view you can take. Yeah, let me get to that in a minute, though. Yeah. Is everybody happy with this point of view first? Yeah, so let's talk about the cylindrical point of view. Different way of saying this. What happens when you convert to cylindrical? Well, when you convert to cylindrical, every x turns into r cosine theta, and every y turns into r sine theta, except here's the thing, you don't really actually have to bring the trig into it. You can, in advance, look for stuff like this, and everywhere you see that, you can just say, okay, well, that's r. and you don't have to bring in trig at all. So if x and y appear only like this, then all of these, they turn into r's with no thetas. The only variable that remains to consider is z, which is already a cylindrical coordinate, right? And so we've successfully converted from rectangular to cylindrical, and theta didn't show up. And we've previously discussed that if you have a cylindrical equation that has no thetas, then it's rotationally symmetric. We talked about that a couple days ago. Yeah. Okay, all right, so pick your favorite point of view there. The reason we care about this is because of this point. If you have a surface that has this rotational symmetry, then there's an easy way to manufacture it. Right? Things that are rotationally symmetric, you can manufacture by taking a cross section in any plane containing the axis and then rotating that around. Right? So, for example, if I were to have a rotationally symmetric, like a bowl, let's say, right? Well, that's a three-dimensional surface. But if I look at a slice of it, that slice containing the z-axis rotates around to make the whole bowl. Right? So any one slice tells you the whole story. You just have to rotate it around. So let's see that in action. Here we go. Here is this surface. You may recall we previously discussed this surface here. Right? I claimed that it was a bowl. Here's how we're going to see it. X and y appear only in the special form. Okay, now, quibble. Where's the square root? Isn't there supposed to be a square root in here? True. Note, though, I can rewrite this as z equals square root of x squared plus y squared squared. And so x and y, in fact, do appear only in the special form, and so rotationally symmetric. So little, slick moves like this, where you sort of rewrite things in a different form, perfectly fine. Is that cool? Everybody happy with that? Okay. So this is rotationally symmetric. Whatever this thing is, it's rotationally symmetric. I'm going to look at its cross section now in a vertical plane. Now keep in mind the rule. I can look in any plane that contains the z-axis. After all, I have a rotational symmetry around the z-axis, right? So I need a plane that contains the z-axis, yeah.
If you had e squared plus y squared, or the square root of that, would that be rotationally symmetric around, I don't remember, whatever variable it is?
Yeah. Yes, I know exactly what you're thinking, and absolutely, and I'm going to get to that on the next page. Yep, it's a great thought, absolutely. Okay, rotationally symmetric around the z-axis. I'm going to pick this YZ plane, by the way, for no particular reason. You've got a lot of options. If you really wanted to, you could pick the XZ plane, or if you're a masochist, you could pick this, diagonal plane like that or something like that. It's just going to make your life harder. There's no reason to want to do that. So let's stick with the easy one, just because we can. And so YZ plane, otherwise known as x equals 0, which I can plug into the equation. And notice what happens. Because I'm looking at this cross-section, because I'm specifically insisting that x be 0, my equation changes into something much nicer. It changes into just z equals y squared, which I instantly recognize as a parabola. Right, high school algebra. And once you know you have a parabola, game's basically over at this point. I know my thing is rotationally symmetric. I know the cross section. I literally then just take my geometric intuition and rotate that cross section around my axis, and that produces this bowl. Everybody buy it? It's a really neat move. Really powerful tool. By the way, this is called a paraboloid. That's just semantics. It's one of these things you have to know, though. Okay. Here's another example. What are we going to do with that? By the way, this one's not a graph, so I can't, I can't think of whatever whatever intuition you feel like you may have gotten from the last example being a graph of something, not available here, right? Still though, equation. Still rotationally symmetric around the z-axis. Still, I can pick any plane that I want. Now, just to show that I can, I'm going to pick the xz plane this time, otherwise known as y equals 0. Whatever. Pick any plane you want. That makes your equation turn into this, whatever that is, x squared minus z squared equals 1. I hope y'all remember your high school algebra. They called it Algebra 2 when I was in high school. I don't know if they still use that name, but the advanced high school algebra, I guess you'd call it. That's a hyperbola, right? And it's this hyperbola right here, like that. So again, rotationally symmetric. I have a cross section. Now I just have to use my geometric intuition and ask what shape gets generated if I rotate this around the z-axis. And, well, it's going to be something kind of like this, whatever that is. Anyway, it's called a hyperboloid, being as it is a rotation of a hyperbola. Seems like a reasonable choice of words. Specifically, a hyperboloid of one sheet. We're going to momentarily see another example. Yeah. Yeah, so that's this key observation is that x and y appear only in that special form. There's no other x's or y's anywhere in the equation. It's just square root of x squared plus y squared and no other x's and y's anywhere else. Yeah, that's the awesome foot in the door on this. Okay. All right, next example. Somebody asked a minute ago, does it work for around other axes? And here's that statement. The short answer, yes. And it's exactly what you would think by analogy. Again, I think here's a really good exercise. Again, you don't have to do this, but I think this would be good to, if you want to make sure that you really do understand this argument, try to adapt it to make a theorem about rotational symmetries around the x-axis or rotational symmetry around the y-axis. Right? And anyway, the results turn out to be exactly what you would expect. And here's a for example. Let's look at this equation right here, in which it doesn't really quite leap off the page at you that y and z appear only in the special form, at least not until you rewrite it like this. And now you can see the y and the z appearing only in the special form, and so we have a rotational symmetry around the x-axis. Again, the details of that argument, why is it that this is the special form, and why does that give you a rotational symmetry specifically around the x-axis? Fantastic little exercise. Think it through. If you get stuck, come to office hours. I'm happy to help you out with it if you get stuck. Right, okay, so rotationally symmetric around the x-axis. Here's our x-axis. Now again, I get to pick any plane that I want. Oh yeah, question?
Why are you saying z equals 0 and in the previous example you said y equals 0? Is it just
Yeah.
the components under the square root?
Don't think about it in an algebraic sense. I wouldn't know how to... I think any algebraic rule we could make along those lines would be prone to misremembering and messing up. The point here is you can pick any plane that you want that contains the axis of rotation. So I picked this one, but I could have just as well picked this one or this one. Take your pick, any plane that contains the axis of rotation. So the reason I picked the XY plane is just laziness, I guess, as the easiest one that I could imagine. Does that make sense?
So what does the setting z equals 0 do, like visually here?
Yeah. So step one. Whoa! I didn't do that.
But yours.
What?
But
In the
do you
okay?
know what's not okay?
The Apple TV took over there. That was not on my computer at all. I don't know what that was. I didn't realize we have an Apple TV in this room. That's actually kind of cool. Yeah, I'll have to look at that later. Okay, so so what's the deal with z equals 0? We identified the axis, right? The axis is the x-axis, and then I look at this picture and I think to myself, what's my favorite plane that contains the x-axis? And I could pick any plane that contains the x-axis. So I don't know, I pick the xy plane just because why not? And then algebraically, once I've decided that I'm going to pick the xy plane, algebraically I write that as z equals 0.
Oh, right. Okay,
Yeah.
okay. I think I understand.
Okay, cool. Okay, so again, once we've got z equals 0, we plug that into the equation and see what happens. And it turns our equation into that, which again is a hyperbola. Something like that. Again, that's the cross-section of a rotationally symmetric thing. So I can generate my surface just by taking this cross-section, and now I've got to figure how do I rotate that around the x-axis, geometric appeal, right? Think to yourself what happens when this orange curve rotates around the x-axis, and it makes I've never really found a satisfying description of what this is. The closest thing that I have to satisfying is I feel like these each look like a contact lens, right? So I call this the staring contest. Anyway, it's still a rotation of a hyperbola. It's just it's a rotation kind of in a different way, and so we still call it a hyperbola. Sorry, I used the wrong colors there. Sorry. It's still a rotation of a hyperbola, so we still call it a hyperboloid, but to distinguish it from the one above, we call this a hyperboloid of two sheets because it does have two entirely disconnected sheets, they call them. Yeah.
So like when you do like rotate around the x-axis, hypothetically both of those surfaces are open and kind of would like extend to infinity?
I'm sorry, I'm not understanding.
Because when you graph I guess like those hyperbolas on there, they would extend out to the
they
so
extend.
The shape when you make it would actually
It extends infinitely. Yeah, I mean, when we draw a thing, I mean, we just don't have the space, right, to draw the whole infinite. Yeah, so we always draw just a portion of whatever. So yeah, these do extend infinitely, sort of out this way and sort of into the. Yeah, sure, absolutely. Okay. Here's the next little tool for your toolbox. Sometimes you want to understand what something looks like. For example, here, want to understand what this thing looks like. What is that surface? And I could do this, right? We could use our rotational symmetry argument here, and that'd be a foot in the door. But let's just suppose we hadn't noticed that. Notice that this looks an awful lot like this equation, which is so much easier to understand. That just says distance from the origin is 13. That's a sphere, right? No problem. Nothing to it. So much easier to understand the green surface. Okay, so instead of asking, what is this orange surface? I'm going to ask a different question now. I'm going to ask, what happens to the green surface when everywhere I had a z, if I were to replace it with 2z? Right? If I were to, everywhere in my equation that I had a z, I replace it with 2z, what does this blue action do? What's the result? What is that geometrically, right? That's going to do what to this green sphere? It's going to turn it into, it's going to transform it, deform it, in what way? Right? So the big idea then is I don't have to kind of reinvent the wheel. I mean, I don't have to view this as being a surface. I start at square one, right? I can say, hey, this is clearly connected in some way to a surface that I already understand. So I'm going to take this as a starting point, and now I just have to understand, what is this blue action? How does that tweak the surface? And now here's my argument of what it does. Notice that I could take a point like this, for example, that satisfies that equation. That's this point 3, 4, 12. satisfies that equation and it doesn't satisfy this equation. Well, of course it doesn't. It's a different equation, right? The 12 was supposed to get squared in here, if you will, in some sense. But if you take that 12 and you plug it into here, then that 12 gets multiplied by 2 first, and then I'm not squaring the 12. Now I'm squaring a 24, the arithmetic went off the rails. Okay, so putting that 2 in there screws up existing points. But you can kind of, reverse engineer the problem and say, okay, well, yeah, fine, 3, 4, 12 doesn't work anymore. But if I were to cut that 12 in half, now let's look at 3, 4, 6. That 6, the very first thing that happens to it is it gets multiplied by 2, becomes the 12 that I was very happy to have here getting squared, right? So the 6 becomes a 12, which gets squared. I find myself doing the exact same arithmetic that I had been doing on the other side. That makes sense? So the punchline then is that when you have points on your original surface, this action of replacing every z with 2z effectively takes every point on your surface and it cuts the z coordinate in half. So, said differently, replacing z with 2z squishes your surface vertically by a factor of 2. Or the way I like to say it, whatever you do to a variable in an equation, the opposite happens to the surface. You replace z with 2z, the surface gets, the z coordinates are half as big. Everybody buy it? Okay. All right, so various examples of this. Here's a nice one. Now again, let's look at this equation there. How would I understand this equation? By the way, I don't really have very many good options here. I can't say, oh, this is a rotation of something easy. It's not. This is not rotationally symmetric at all. There is no pair of variables in here that appear only in the special form. There is no rotation argument to be made, right? Losing. Okay? This is not distance equals constant. It's just not. Right? These A, B, and C down here are kind of messing things up for us. What I can say is that this is a tweak of this equation that is super easy to understand. And the tweaks specifically are everywhere I have an x, I replace it with x over a. Let's see here. Oh, color choices. Everywhere I have a y, I replace it with y over b. And everywhere I have a z, I replace it with z over c. So 3 algebraic tweaks, 3 algebraic, you might say, replacements, right? And each one of these causes a geometric deformation. The act of replacing x with x over a, what's the opposite of dividing by a? Well, multiplying by a. So this algebraic replacement, replacing x with x over a, is going to stretch by a factor of a in the x direction, and thus the a at that point, likewise the b at that point, and the c at that point. Right? This original unit sphere just gets stretched by different amounts in different directions, and ellipsoid. Everybody okay with that? A couple other examples you can notice here, and again, notice in each of these cases, I have questions I don't know how to answer. On the right, they don't have rotational symmetries. I got nothing that I can sort of work with. These, however, I've already studied. I already understand those. And so if I want to understand these orange ones over here, all I have to do is ask, well, how am I tweaking these, right? I'm clearly going to be deforming these green surfaces that I already understand deforming them in certain ways to make these orange ones that I'm trying to understand. And you just keep track of the deformations. Now I'm going to show you one little algebraic little trick here. Let's look at this first one. A lot of people get the wrong tweak. A lot of people will see this a squared down here and think, okay, well, I guess I'm dividing by a squared. But you're not. The question is, what do I replace x with? And whatever it is that you replace x with, your equation is going to become z equals whatever you replace x with squared plus dot, and what you're going to be replacing x with. What do I need to put in here so that when I square it, I get x squared over a squared? Notice it's x over a. It's not x over a squared. Everybody see that? This is a nasty little landmine that a lot of students step on. And so always be on the lookout for this. Think very, very carefully. It's not about what you do to the equation. It's about what you replace one of the variables in the equation with, specifically. Okay. All right. And we move along. So that's section 2.1. We're skipping section 2.2. It's sad necessity. I've mentioned before this class moves at breakneck speed. Perhaps you've noticed. And it's going to be going faster, by the way, as time goes on. Sorry about that. It's the nature of the course. 2.2 is very cool material. Mathematically, very important material. But in a kind of a mathematician proofy rigor kind of a way, and not really very much in a Math219 kind of a way. So sad, but we're going to skip 2.2. And moving along to 2.3, we're going to talk about derivatives. The first thing I want to mention is there are multiple different kinds of derivatives for multivariable functions. Not so with single variable, right? With single variable, there was the derivative. That's it, just the one. We're going to see a bunch of them, 4 or 5, that make sense and get interpreted as derivatives. They play kind of roles, kind of like a single variable derivative in their different ways, in different contexts. So do be on the lookout for all these several kinds of derivatives. I will point out that there is something a little sketchy about using the same word to describe lots of different things, right? If they're different, shouldn't we give them different names? And we do. So, but what is it specifically? Why do we use the word derivative in relation to several different things? What do these things have in common that makes them all derivatives? And this is it. They relate input changes to output changes in their different ways. All the derivatives we're going to talk about, and every interpretation you have of derivative in a single variable context, in their different ways, relate input changes and output changes. So that's just a broad stroke foreshadowing, something to keep in mind as we move through this chapter. We're going to start with something called a partial derivative. I imagine some of y'all might have seen partial derivatives before. It's a good place to start because it's easy. It's familiar. And logistically speaking, we kind of have to, because that's the order that the book goes in. And I've in the past gotten taken an aggressive point of view and reordered the topics in a way that suits my preferences, and it creates tons of confusion. And I'm just not going to do that in this case. It's too hard to do that. So we kind of have to. So now that said, even though these are very easy to understand, they're very relatable and familiar from single variable derivatives. Huge point here. This isn't really the best point of view on differentiation, in my opinion. I think there's really a much better way to think about derivatives. than partial derivatives. Partial derivatives serve an important role. We need them. It is very, very valuable that they're so easy to compute. They're good things. I'm not anti-partial derivative. But I just don't want you to think that this should be your cornerstone point of view on derivatives in this class. It really shouldn't. It'll take us a couple of days to get to what I think it really should be your cornerstone point of view, but we'll cross that bridge when we get to it. Here's how you compute them. It's not that much to it. Got a multivariable function. Just hold all the variables constant except for one. And this is kind of seems maybe a little bit silly, I suppose. Are we allowed to just say that variables, which by their very nature can change, can we just say that they're constants? And, well, yeah, we can. It's just that what we interpret from having made that choice is very limited. It's very limited to with the understanding that all these other variables are, for the purposes of this discussion, not allowed to change. Right? So this is one of the reasons I'm cool on the question of partial derivatives. There's something a little highly limiting about them in this sense. Still, let's treat them as constants. I had several variables. Now I really only have one variable left. So my function of several variables is now effectively a function of a single variable. I have a single variable function, and I know how to take derivatives of single variable functions. I'm going to show you an example momentarily. Real quick on the notation, though. This is our kind of main notation. It looks like Leibniz notation for derivatives. Importantly, though, this symbol right there is not a D. You can't use a D as an alternative. It's not a personal choice, right? This is an important distinction in standard mathematical notation. So highly, highly not optional. You cannot put a D in place of this weirdo little symbol. This is a brand new little weirdo little symbol that, again, silly though it seems, it's a healthy exercise to kind of practice your pen stroke and make sure that you can draw conveniently. Likewise, commonly misunderstood, sometimes students think it's a Greek letter delta. No, Greek letter delta kind of flops over to the right at the top. This doesn't. So it's a new symbol, and again, take your time in learning how to draw it. Easy to compute. Super easy to compute, in fact. Look at this seeming nightmare of a question. We're going to take the partial derivative with respect to y of this great big monstrosity, which is a product with a composition of another product. And you may look at this and think, oh gosh, the tedium, it looks like this is going to take a page or something to write the whole thing out. And it doesn't. This is actually a really easy question because all of this stuff here full of x's and z's, and x and z are constant. Right? Keep in mind, for the purpose of a partial derivative with respect to one variable, the other variables are all constant. So what I've got here then is really just the y partial of y squared. And the y partial of y squared is just 2y. And all those constants, again, they look like variables, right? But they're just constants, and they just come along for the ride as constants do. Super easy to take derivatives. Is everybody with me on that? A couple other examples down here. We can do this real quick. A couple other examples. Again, this first one looks hard because, let's see, I'm taking the x partial of something, but keep in mind that means that y is constant. So this is not a function to the power of a function. As far as an x partial is concerned, this is a function to the power of a constant. And it's that easy to compute the derivative. Plain old single variable calculus. Likewise, if you're taking a z partial down here, then all of this is constant. And I have merely an exponential constant to the power of z. And again, that's a standard single variable calculus formula. Okay, this is a great place to draw the line. We will pick up here on Monday. Y'all have a good weekend. See you later.